Alrighty, we've got Mike giving us a lecture on electronic blasting. Thanks, Mike. I'm looking forward to this.
Okay, all right.
Without any further ado, over to you.
Thank you. So, yeah, my name is Mike, VK2UCT. So, I'm going to just talk to you about the use of electronics or recent developments of electronic systems in blasting. Okay, so what we're talking about here is commercial blasting. This is mining, quarrying, construction, building roads, knocking buildings down, and stuff like that. So I'll just tell you, I came to this because I'm actually not an electronics person myself, I'm actually a chemist. So I studied chemistry, did a PhD in chemistry, got into explosive research, working for ICI, as it was globally, and eventually in Orica. So I sort of came to all of this via chemistry, and in fact, traditionally the explosive industry has been all about chemistry, and in fact initiating blasts it's all about chemistry, and it's all now changed and become highly electronic driven. So that's why chemists were in control of explosives and not electronics people. So I will be talking a bit about the electronic business, gizmos. I've got some information on how it works. It's very basic and I don't really understand it all, but I thought I'd just give you a flavour of it. Okay, so what I'm going to do, I'm going to give you a bit of introduction to how blasting works and how things are timed. So we're really talking about timing, because when you're in a mine, you don't want it all to go bang all at once. Like if you want to blow up a building, you just go bang. When you want to fight a war, you want big bang quickly. In blasting, you're talking about timing. So we're talking about how we sequence and we time blasts. Okay. So now, left one, Eve.
Is that the video?
So yes, this is the video. So I'll just, by way of introduction, I'll just play this video, which I think is going to work. Oh, we'll look up there. Let's see how this goes. How do I get the video to work? So click that. Tick.
This might start there.
You might start there.
Okay.
You hear it? It's going to be sound. So this is just some examples of different types of blasting. back to this? Eve, how do I get back to the
Just close that window.
okay. Don't want to see it again. Okay, so that is obviously a YouTube clip from a commercial explosives company, Dyno-Nobel. That's the second biggest company in the world, and it is in Australia. So what? So one thing you'll notice with blasting, you'll notice there's no flame. You know, there's no fireball. Okay, and that is because real explosives go off so quickly that you can't see it. If you slow it down enough, you might see it. So in movies and so on, it's not real explosives, petrol bombs that they're setting off. All that black smoke and all that flame, that's not real explosives. The explosives themselves are basically loaded into boreholes from a truck that looks like that. It's basically, the mixtures are seen in the back of the truck and they're pumped into the boreholes. These mixtures are mainly based on ammonium nitrate fertilizer. And so, you know, there's literally tons of the stuff that is pumped in and the blasts go off in a defined sequence. Okay. So, so what we're going to talk about, I'm not going to talk about the explosives, I'm really going to talk about the way those blasts are initiated and timed. Because you can see the timing effect through those blasts. So the sort of most common system that is used looks like this. What it is that's the detonator. So that's the bit that initiates the charge down the hole. And this is a kind of a fuse, which is called shock tube, where a high explosive signal shoots through the tube at about 2,000 meters a second. It doesn't actually blow the tube apart, it's just a way of transmitting the signal from some sort of connector device. And so in order to initiate a blast, you basically connect these things together like plumbing. And you connect them together and in a sequence that it'll be set off. So this is an example of one which has been connected up in an underground situation.
Looks a bit like my wife's pot plant watering system, like.
Sounds like too, Russ.
But when it goes off, there's no watering system there. Okay, so the thing to remember is that all of this existing system is pretty much based on chemistry. Okay, so let me show you. So basically, that is what a detonator is, and so this is the thing that sets off a blast. And so you've got some sort of aluminium tube. You've got this. This is a plastic tube, which is like a transmission device to send a little flash down the tube to initiate the detonator. And what you've got in here is what we call delay elements. And so what they are a little, usually a lead tube with a pyrotechnic material, fireworks material in it. And this material here burns at a very defined rate. So the length of that piece of tube gives you your delay time. So the composition, the material that's in there, you know, how fast it burns effectively, and how long it is, that gives you the delay time. Okay? And when I talk about delay time, all of those pictures that you saw earlier, the timing between the holes going off were around 500 milliseconds, half a second. So that, you know, they go quite short. They can go down to 25 milliseconds. So we're talking about millisecond blasting here. So these things, so all of this is ancient Chinese technology in there. It's basically fireworks technology that's been refined over a very long time. But it's all based on chemistry, and it's pretty much a black art that companies have learned to do over the years. So that is what a detonator looks like. Now, in terms of, you know, if you want to be a terrorist, you can make a bomb quite easily, but this is the thing that sets it off. And detonators are very highly controlled because you have to have a detonator to create a shot. So that's why, from a security point of view, they monitor very, very careful. And they count it and make sure we don't lose any. You never know where they end up. Okay, so this just shows you how these things work. So basically, a signal comes down the tube, and what that signal will then do is run through the delay element, and in the bottom of the detonator is a little charge, and that charge will then accelerate and fire that next charge.
So the signal that's coming down, that's basically a very fast burning lining almost of the signal.
That's right, so that's plastic tube with a little coating of explosive in it, and you give it a bang on the other end, and that signal transmits down the tube.
So that's explosive rather than pyrotechnic.
It's explosive,
Yeah,
yes. Yeah.
to move that fast.
Yeah. This is actually called signal tube or shock tube.
Yeah.
So it was a technology that came in the 80s, and Australia took it up with gusto. In fact, Australia was probably the leading country in the world to adopt this technology, and it's still very widely used. Okay, it's probably the mainstay of how blasts in quarries and mines are initiated. But the electronic systems are coming through.
Is that sorry, is that a one-use liner?
Yes.
Right.
Because remember, that detonator sitting down could be in a 30 or 40 metre hole in a coal mine. Okay, so you don't see anything. The only time you see something that doesn't go off. Yeah. And I should say, some of those shots, and I'll show you another video of a coal shot, which the sort of thing that happens in the Hunter Valley. These blasts are so big that they do register on the seismographs that they've got around the world, to see that nobody cheats on the nuclear disarmament treaty. Okay, but because such a blast takes even though it's over quite quickly, you can see the individual holes going off, so they know the signature of the blast, so they'll know a Hunter Valley coal shot from a North Korean nuclear.
So all South Koreans, I mean. So.
Yeah. Yeah. So let me just, I'm just going to show you another little quick video which is embedded on how this works, okay? So just...
Try it.
See it come on the media, it is there. I'll just skip that one and come back to it, okay? This sort of explains it. So in those blasts, you notice that there was a lot of dirt being thrown, okay? So all blasts are pretty similar in the sense that you have this is called a bench, and you drill holes in the bench, okay? And you put your detonators and your booster charges in the bottom, and what you want to do is you want to initiate at that point, and you want to sort of peel off each row by row, okay? So you want to peel this row off to make space for the next one to go off. That's why you have timing. Because what they want to do is they want to throw all that dirt away so you can dig it, and usually underneath here is a coal seam, for example, or an ore body. So what you're trying to do is you're trying to remove the dirt on top of the ore body with a coal seam. And that's what we're talking about, throw blasting, okay? So this should work. So what the important point is this is the millisecond timing, okay? So that one goes off immediately, 100 milliseconds later, that one goes off. The detonator goes off, okay? And so what you do is you initiate a whole lot of holes back here before the first detonator fires, okay? And that's what we call a burning frame, okay? Because what sometimes happens is this stuff can shoot backwards and it could cut off the initiation leads. So what you want to do is you basically want to initiate a whole lot of holes right back before the first one's initiated, okay? So that's what's called a burning frame. And these are all, so this is milliseconds, okay? So these ones have those detonators effectively been initiated, and they're timing. That little element in there is burning away, and that first one will go after this one has been initiated. It's about 400 milliseconds before the detonator goes off. That's how it works. Very, very, it's quite simple, really. So let me just show you. So this is a good example of, now that you sort of know well, I'll show you, this is what's called a cold throw blast. So this is what happens typically a lot in Australia, Hunter Valley and Queensland. What they're trying to do is you're trying to, so down here is a coal seam. What you're trying to do is you need to throw all that dirt. You need to throw it away, and then you can get in and dig the coal, which is soft. So let's see if that is going to work. So did you notice that bright red was coming over? Did you see the fireballs?
Yeah.
That is coal dust initiated. So the blast sets the coal dust up. You know, there's a bit of coal dust mixed in, and then it.
Like the next video.
Oh, you'll see this one. Oh, how do I kill it?
Two different
Sorry. Oh, it's in the background. Yeah. Oh. How do you feel that one?
Just a little bit.
Press escape. Yeah.
Oh, okay.
Press escape and get out full screen.
It's got to be
Then you can
easy
smile.
flowing. Okay, so that's just a bit of background on how it works, okay? So, as you can see, we do have quite a lot of fun with this, okay? So having talked to you about the sort of conventional detonators, and when you think of detonators, you remember the old movies when John Wayne's throwing a hand grenade, right? Pulls the pin and he throws it, it doesn't go off straight away. Allows the hand grenade to get away. That little timing element in there is exactly the same as what's in a detonator. It just allows you, gives you a bit of time to let the hand grenade be away. In this case, it's a little bit more accurate. So this is an electronic detonator, okay? So having said to you before that it was all based on chemistry, this is electronics now. So everything's pretty similar. There's a tube, there's a little charge at the bottom, and then there's a little electric match head. This is like a small element that if you put a current through it, it'll heat up, and there's a flash composition in here which will then set that off. Okay. So an electronic detonator is a very simple thing really. It consists of a circuit board, a PC board with a microchip. This is actually a South African design one. So there's a microchip that sits in there. It's encapsulated in a shock resistant resin, protected, and it's a custom designed chip. And then sitting over here is a capacitor. Okay, so that blob is a capacitor. So if you look at it here, this cutaway sketch, and it's got two wires coming in. Okay, so this is all electric now. Before it was all what we call non-electric. This is electric. two wires coming in, connected to the circuit board. There's some input resistors. There's a capacitor that sits there, and underneath it is the chip. And the chip, what the chip does is it communicates with the network, as I'll show you, and it controls the timing. And the energy to fire this thing so basically what you do in order to fire it, you charge the capacitor. The capacitor can, you charge a capacitor, the capacitor can sit there, counting down for up to about 15 seconds. And then it will then fire, it will then send a pulse to that fuse head and initiate. So that's what electronic detonator looks like. So one of the interesting things about electronic detonators is they generally encapsulate in a copper shell, whereas normal detonators are aluminium, because you can imagine that in that blasting situation there's a lot of shock waves that are flying around, and some of these things get completely flattened. And so copper tube is a lot tougher, doesn't get flattened. So they're generally copper shells. Okay, so what they look like commercially is that. So here's your detonator, wires on a spool, and then there's some sort of connector at the end. And so what you do is when you hook them up, it's literally try hooking up a computer network. So you just clip these onto a harness and to some control equipment. The control equipment communicates with these. So each of those detonators the chip has a unique ID. Each detonator has a unique ID. So the system knows, you tell it where the detonator is, and you tell it what time it needs to go off at. So with that detonator, there's two basic bits of kit. Okay, there's this something that looks like this, which is called a logger, and this is the blasting machine. Okay, so what happens is when you lay out your shot, you basically, as you're hooking it up onto a harness with a connector, you either read a tag or you connect it, and that logger will read the unique ID from each detonator. It'll also, you can then also program the delay time into each detonator. So you can tell each detonator when to go off. Okay, so you've got really infinite possibilities on how you want to time your blast. So that piece of equipment is a testing device. It communicates, and these detonators communicate two-way, right? So you talk to the detonator, and the detonator will talk back to you. Because what you do is this logger puts some energy into the capacitor to power the chip, so the chip can communicate. Okay. So it's a full two-way communication. So if you've got a big coal shot that runs a couple of kilometers that way, you've got 1,000 detonators. This is like a big network, and you're communicating with these logging devices. And then when you want to fire the blast, you go a long way away, and this is the box that will do a big final test. Is everything connected? The great thing about this is that if anything's not working, if one detonator is faulty or there's a break in the cable, this system will know there's a problem and you can fix it. It's a fully testable system. Whereas there's other things you just got to hope for the best. The guys have connected it correctly. Okay. The great thing about this is that you can now actually, there's blast design software which is out there. So you can actually, so this would be looking down on a particular shot. So you might want to set this bit off first and then that bit. So you can actually design your blast in a CAD system. And then you can you could decide what sort of blast effect you want, what sort of sequencing you want, and you can then download that into that logging machine, and it will then tell each detonator what the timing is. So you can do some very, very sophisticated and clever things, much more flexible. So this is what happened. This is blasting software is now out there and used extensively. So. Guys, how does this work? So, the electronic detonator, typically has a single capacitor. This one, 22 microfarad capacitor on the chip, basically fires powers the timing circuit for up to 30 seconds in this particular one. So there's enough grunt in that capacitor to keep the thing powered for 30 seconds. Because basically, once you've sent the signal to the detonator, each detonator is on its own. Because all that blasting is going to rip that firing harness. So each detonator is basically sitting there with its power on board, timing down. once you fire the signal. So that capacitor has to have enough current to keep it going up to 30 seconds. Okay. So one of the interesting things about this is that this particular system requires a 13 volts to fire that match head, okay? But the testing, so think about the testing device, you are actually sending a signal to, when you're testing, you might be standing over the hole, might have a ton of explosive in it. They're testing it. You don't want the damn thing to go off. So what they do is these logging boxes or testing boxes generally have a 9-volt battery in it. They do not have enough energy to fire the system. The inherent safety is in there. Okay. The other thing is these things do not contain the encoded firing signal. Okay. These things have a specially designed, and I'll talk to you a little bit about it. Communication protocol, so that it's not going to pick up somebody's Wi-Fi. It's not going to get contaminated, if you like, with some other communication things that are happening around. So these boxes are designed as a testing device. So they obtain it, when you connect it, it reads the ID of the chip, so it knows in that hole that chip's there, so you can give it its delay time. So you can assign it full delay time. And it's full two-way communication. So if there's a fault there, the detonator's faulty, or there's a break in the cable down the hole, it'll tell you, and you can replace it if you need to. So it's pretty smart in that sense. Now, guys, you'll have to read this. So the communication protocol, I understand, for these detonators, and this particular product was developed in South Africa, and Orica use it, and Dino use it. So the interesting things, these connections are non-polarity sensitive. So it doesn't matter which way you connect them up. Okay, and I understand that the messages are sent along the harness in terms of symmetrical voltage swings. So, having read that, guys, does that make sense?
So
Do you understand? Do you understand?
13 minus 13.
Yeah. Do you understand what that means? Yeah, excellent. Okay. So that's how the thing communicates, okay? I'll give you just time to look at that. Okay? When you're going to fire it, so remember you test it, you give it the delay time, and then you take this other box, which is the firing box. And that's when you stand a few kilometers away because you've got to be at a safe place, okay? You either have a very long cable, or these days they have a wireless connection. And so this box will then send an arming signal to the detonator, say get ready. It'll then fire up the capacitor and then send the firing signal. And then each detonator will then time. Okay. There's no crystals on these detonators, by the way. These are all electronic timing circuits that are on the chip. These things were, there was a lot of work done on them because when an explosive goes off in a hole, think about it, you've got a lot of explosive in a hole, it is a very high, these explosives go off at a speed, so like the speed of the reaction in the explosive is about 5,000 meters per second, right? 5,000 meters a second. They're very high energy events. They generate a hell of a lot of EMP. They also generate, it's almost like a plasma that you've got in that reaction zone. And that generates a huge amount of EMP. It's almost the sort of thing you can expect when the nuclear bomb goes off and it knocks out electronic communications. So the guys that developed this system built in some very clever capability so that it's not affected by those enormous electronic pulses that sometimes even come up the cable if it's still connected. So there's great antennas hanging around in there. So you can imagine it's a very challenging environment for an electronic system to work. And remember, the challenge with this is, if you think about it, and this technology was based on military research, but if you think about it, when in the military, when you're making a missile, you make one missile, it costs a lot of money, and it's got to work. Okay, so it's small volume, high standard, high technical challenge. Okay, these things have to perform very well and reliably, but you make them by the million. It's a completely different sort of situation, and you've got to sell them for $10 each. Yeah, not $5 million for a cruise missile. So it's, you can see that it wasn't a trivial exercise to get this technology into the marketplace. So as I said, this is the blasting. It's connected to the blaster. The blaster is the only one that has enough energy to initiate the detonator. So generally, the people who can fire the blaster, shot firers, these are people, you can get your shot firing ticket, which allows you to fire explosives. And generally they have magnetic keys and various kinds of safety devices. The shot firer keeps with him or her all the time. Because you wouldn't want somebody connecting this up and always still working on the blast. Okay, so the safety protocols and the procedures to make sure the testing and the firing are completely separate. Okay, how's that so far?
Good.
All right. So what I'll do now is I'll show you some videos of electronic detonators going off versus conventional detonators. Okay. Now the thing about electronic detonators is you can program them, so you can have lots of delays. Whereas conventional detonators, you limit it by the length that you can cut that little bit of rod and the powder. Okay. But the other thing about electronic detonators is they're very, very accurate. When you're dealing with fireworks and you're cutting it on a lathe, the length can vary, so you get a lot of delay scatter, variation in timing. Okay, so much so that you can actually hear it, right? So you can hear the difference. So what I'm going to show you first, and this is on a test range up in Queensland, where we used to work on these things. So there's 1,600 electronic detonators, millisecond delays. So they've just laid them out in a paddock. And row by row, they're going to set them off. And you can hear what that sounds like. I'll do it again if you like. So you can see those rows.
Yeah.
And I think this one, they've just daisy chained it all together, okay? So, you see the wires flying around? They're all buried, just pushed in the sand. So, that's how we used to test these things. And if you put a high-speed camera on, you can actually see that it's working very well. Okay, so let me show you another demonstration. Okay, and then this time I'm going to talk about demonstration of tunneling. Okay, so I'm talking now. So before I was talking about blasting coal mines, what we call open cut mining. This is development blasting or tunneling. Okay, so this is what happens in underground mines. In order to get to the nickel or the gold or the copper ore body, you've got to put tunnels underground. Okay. So this is like a typical tunnel. It's like what they do, it's like a railway tunnel, if you like. These may be 3 by 4 meters. Okay. All these things they blast, in Western Australia they do a lot of this, just blast through the rock to help you get to where the ore body is. Okay. So this is one that's been, and you'll notice there's cables and various things. Down the end there, they'll be blasting at that end because they want to extend this tunnel. Okay. So, a tunnel blast looks something like that. So, can you imagine the end of that tunnel? This is the rock face. Okay. Now, because in a tunnel blast we don't have that bench effect to move the rock away. Okay. So, in a tunnel we want to go that way, so we're going to be blasting the rock this way. So what they generally do is, they drill a series of concentric holes. Okay. So what they do is they drill some blind holes, that's of those, and these are holes that will be filled with explosives. So you see these holes in the middle, and then there's some holes on the outside. So in order to create the tunnel, what they would do is they'd fire these first. These would then break into these and come out. We put enough delay on it so that all that rock is flown out, and then we'd initiate those so the rest of the rock can come out. So what happens in tunneling, you fire these, and then you fire the outer rings depending on how many holes you've got. Okay. Now, because of the fact that that's a very constrained geometry, we use a much longer delay time in tunneling. So we're dealing with seconds rather than milliseconds. So because you've got to give all that rock time to fly away before you fire the next one. If you fire the whole lot all at once, you might bring the mine down because you create just a massive seismic event. So you want to get the rock flying out the way so the next lot can go. Okay? Does that make sense? So what we have here is a simulated face. So this is just a steel plate, holes in it, and this looks like a watering system. So imagine, so the detonators are sort of poked through the back in little tubes, and this is what it sounds. If you were standing there next to a tunnel, if you survived, this is what you would hear. Okay.
But that's without the charge, just...
No, without a charge.
Correct.
That's just a detonator, okay? And I should say that a detonator contains about 1 gram of explosive. Okay, so 1 gram of explosive. If you held a detonator in your hand and it went off, it would, completely destroy your hand. The worst thing about detonators going off is the aluminium shrapnel. So eyes, you get peppered if there's an accident. But it's only a little charge, right? So that's how it sounds with 1 gram. When you've got tons, it's not different.
I'll stick to the push point.
Yeah. By the way, it doesn't normally have music with it when it goes off. So listen carefully to this and see what you think. Here, I'll give some. I'll do it again. So just listen to this. It's a bit erratic. You see the stuff in the middle? And then the other ones? That's what a conventional, so those are what they call long period delays. They go off, in the order of seconds. So if we do the same thing again, and this time now we've got our fancy electronic detonator. So we're doing the same effect. It's starting to blast in here, and progressively going outwards. So you see those rings are all, the little ones are going boof, then the other ones boof. So on, so it's much more, there's less scatter on it, okay? So one of the advantages of that is that all these blasts going off in mines, they cause a lot of vibration. And if you live in like Broken Hill and they're finding blasts, the whole town shakes. So what the other guys can do in certain sort of mines that are seismically sensitive, in other words the rock's a bit unstable, they can actually design the shots to tune the frequencies that they're putting into the rock to minimize seismic activity. So that's what electronic detonators can do. You can actually tune the shot.
So you can't do it in phase reversed, so it actually cancels it.
No, you can, actually I think there is some work with the guys choosing different delays to do that very thing. And the whole area of vibration monitoring and blasting is a whole science in itself. But these systems have allowed people to kind of do those sorts of things. Where this has become particularly important is in quarries. Okay, because quarries are just a little bench blast. But a lot of quarries are now very close to population centres. And the neighbours don't like it when you shake the windows. So you can tune the blast to reduce the vibration effects. And that's what electronic detonators can do. So, guys, I think that's nearly there. Oh. Yeah, this
Hang
one.
on,
Okay, you see this? You see this?
oh, yeah.
Probably.
Play it.
Yeah,
Play it.
So let me just say, just before we do this, so Australia has really been on the forefront of the development of this new technology, and you know, ICI and Orica, you know, were the leaders. A lot of the technology actually came out of South Africa, and ICI then bought the South African company, had a collaboration with Germany, and you know, these electronic systems are starting to come in more and more. Okay, they still cost more than the old system. And the mining industry is incredibly conservative, and the mining, you know, miners are tough, crusty guys. They don't like to change. So it's still quite a long way to go for the electronic detonators to get in. One of the problems with electronic detonators is the wires. You know, you're putting wires down a hole, the rock's moving, it gets cut off, you get sharp, you know, pieces of rock. So it's still quite a challenge to make them reliable. But they're certainly coming in more and more, and people like Rio Tinto, for example, use them quite extensively now. So, yeah, so I was involved in the project to bring that system to Australia, not from a technical capacity, but as part of a technical team that was working on it in Germany and Canada and US. And we were kind of the first cab of the rank. And we trial a lot of these systems in different applications to see if they can work and to see what you can do with them. Yeah.
When you're dealing with your example before, a 2 kilometre wall, 1,000 charges, how do you know if one doesn't go off, and what's the implication of that?
Well, often, well, you know, if one doesn't, what often happens is they go out of sequence, okay? So let's explain. So if the timing is all screwed up, then, you know, we've got to move the rock so one goes off too early, okay? And what they generally notice that is if there's big boulders, because you see this blasting relies on two things. It relies on the kind of shock wave from the explosive going off to break the rock into bits. And then there's the gas that comes behind from the reaction products to move the rock. So generally, if there's something goes wrong, you can see it because they can't dig it. Yeah, they've got a big boulder there. Okay, if something doesn't go off, then when they're digging it, then they find undetonated explosives inside the rock pile.
That would be bad.
That's very bad. It upsets the customer no end. Okay, so that's why you see these systems are not. They're almost to a military spec. Because the reliability has to be that good. It has to be so good that there are no misfires. So generally underground you can bury your mistakes because it's such a narrow, confined sort of environment that if one hole doesn't go off, the shockwave set it off anyway. But when you're dealing with a big open cut coal blast and something goes wrong, you'll dig it out and then you'll get called to come and
Is it dangerous though if they do come across a whole pile of undetonated explosive when they're mining?
Well, you see, the explosive itself is quite insensitive. Okay, the detonator generally goes into a booster charge of one hole, so it like amplifies the detonator is 1 gram, then you put it in 250 grams of a military explosive, which gives it enough punch to set off the main charge. So that explosive, which is like Vaseline, it's like a thick liquid, is actually quite insensitive, and once it's been messed around and it's got rock in it and it's got water in it and it's in the pile of rock, is probably not that bad, and if it rains it'll wash away. But if you hit the booster charge, that's when the problem is. So generally they don't sort of initiate it, but it's not a good thing. The bad thing is if like a whole section doesn't go off, right? So in other words, it stops, and then what you do is, because this timing went out, you effectively don't push the rock in the right direction, you push it backwards on the unblasted part. Then you've got live explosives, detonators, and a pile of rock on top of it. And then you've got to dig it out to reveal the explode, then you've got to set it off again. And that's when all hell breaks loose. Yeah, they, you know, but these days it's remarkable how good it is now, and there's not that many issues of reliability. But yeah, in my career, because I was a technical guy, I was working on the development of the explosive product, and then the field guy calls up, and we've got to go, please explain. You know, why didn't work? But these things are pretty damn reliable now. In fact, what has happened is that conventional system is almost like commodity now, and you know the Chinese are making it, the Indians are making it. It's, you know, you can get it from anyone.
Yeah, in those ones where you had a whole line of explosions going off, how do you work out how far apart to put them? Is that just experience? Like if you put them too close, they'd all go off at once, wouldn't they? One blast the other one.
Yeah. Again, yeah, I suppose that is kind of, well, you know, sitting behind this is also a lot of rock mechanics science.
Yeah.
You know, there's guys that study the way the cracks form, and how much explosive you need to create a crack, and then how much explosive you need to move the rock. And they've developed very sophisticated blast models. So, for example, Orica up in Kurri Kurri's got a big technical centre. They're running some very sophisticated computer models there, which originally came out of the US, out of the nuclear program. Because you know, nuclear explosives are driven by conventional explosives to accelerate the two halves of the uranium. So when the Cold War ended, some of these very sophisticated finite element models were made available outside the military. And so Orica's running these programs, and so they're modelling, you know, how the rock moves, how the boulders are formed, and so there's a lot of work going on to kind of optimise the process. But generally, there's kind of rules of thumb about how far apart they need to be. If they're too close, as you say, they could go off. If they're too close, you could get powder. Now, you can't dig talcum powder, but you also can't dig a big boulder bigger than the bucket that you're trying to dig with. So it's a balancing act. So it's that's why commercial explosives are much more interesting, really, than military explosives. Military explosive, you just want one massive bang because you want to shatter everything. Commercial explosives, you want to shatter to the right size, and then you want to move it so you can dig it out. So you see, this is particularly important in quarrying, for example, because quarrying, what you want to do is minimize the amount of crushing you need to do on the rock, so it's useful for roads or for construction. So you use the explosive to get it to the right size, and then you just bung it through the system. But even underground mining, copper mining, they all have to crush the ore, but they also have to dig it. You know, they have to get it out of the mine so you can put it through the crusher and then through the plant. So it's all a balancing act. And I suppose since the mid-80s, it's got really sophisticated.
So you need exactly the right fragmentation.
You need the exact, that's the right word, you need the exact fragmentation. So commercial explosive is fragmentation and what we call heave. So coal, you just want to throw it. The further you can throw it away from the coal seam, the better. In fact, if you don't have to dig, if you can throw it into the hole you had before and leave it there, you know, you don't need to dig it. Underground, you've got to go in there with a bucket, you know, like a mechanical digger, and you've got to move it into a little trolley thing and then put it through all parts and so on. So this is all about balancing.
How long does it take to set up some of
the big blasts? Those big blasts could take weeks to set up because you've got to drill them all. Some of those holes are 30 to 60 meters deep. You've got to drill them all, and you've got to load them with explosive, and then you've got to come back and fire them. So those shots can take a few weeks. You know, there's millions of dollars tied up in one coal shot.
Presumably they use a computer program to work out delays based on how much earth, what the density of the earth, how deep, all that sort of stuff. Yeah, so.
And these days they're now using GPS to log where the holes are. You know, so the trucks have got GPS, you know, those explosive trucks come along and they've got GPS on them, so they know, you know, where they are. So all of that's happening. It's got very sophisticated. And of course you know that in some mines they've got automated trucks.
Yeah.
No drivers.
Yeah.
There was an incident where a driverless truck drove over a car or something in a mine, so they're thinking, well, maybe we need to have a few people around. So what's happening now, I suppose the new development is there's a lot of radio, they're looking at radio detonators, so no wires.
That's a change, because when you go past the blasting area, there's big signs.
No,
Please turn off your radio transmitters.
Yeah.
Maybe we can have some fun there.
Yeah, radio transmitters they don't like you. But the thing is, I should say that the issue with radio transmitters are not about electronic detonators, because electronic detonators are safer. That's from old days when we had electric detonators, where it was just two wires going into a shell with a match head. You can use a 12-volt battery. So effectively, the wires coming out of the detonator is a great antenna. So electric detonators are almost dead now, hardly ever used. These electronic detonators are actually much safer.
They're coded on.
They're coded. So if you can, if you stick them in the mains, they won't go. You can put them in the main
Unless
socket.
you certain check arm fire.
Yeah. And they've got static protection, so there's they're actually a lot safer. But one of the things that's starting to happen is those early electronic detonators all had custom designed chips. What is happening is people are now starting to make electronic detonators with commercial chips. They're off-the-shelf ones, and there's
In China.
yeah, there's been a few incidences where they've sort of gone.
You wouldn't want that.
No, you wouldn't want that. And there's been situations where they've gone off and the guys got a fright, but fortunately the damage went away from them, not towards them. So, you know, I think spontaneous initiation of detonator and good thing. So the regulator's very nervous because there's just so much new stuff coming along and people are saying, oh, we can make electronic detonator. I mean, every two-peg explosive company now is offering electronic detonator. So they go talk to some Indian programmers and they got an electronic detonator. So that's a worry. So any other questions before we show you the well?
The well.
Yeah, but Australia is still at the forefront of all of this. Orica is, it's an Australian company. Unfortunately, not a lot of the development is done here. No, the manufacture's not done here either. But the applications, we're still pretty strong on that.
Do you work for Orica?
I used to. I used to work for Orica and we had a downturn. So what I now do is I do kind of regulatory compliance and safety. I help the smaller companies work, get their licenses and do audits and things like that. So I'm still involved in the industry. I still work with Orica on some safety related things, but I don't work for them anymore. All right. Have you seen a well? Have you seen a well?
That's blasting.
Well,
It's a good one.
it's a good one.
Is it real?
Absolutely.
Oh,
And it's,
yeah.
this is very
You're
old.
going to tell the backstory to it, perhaps.
I think
They tell you.
They tell me.
They tell you the story.
Yeah, they tell the whole story.
Okay. So this is. I'll just in case it's difficult to understand. So this is a story. I think it's back in the 70s maybe.
It's got the date there.
Yeah.
1970,
yeah.
Okay. In the US, a whale beaches itself on a beach somewhere. So the locals decide, how are we going to get rid of the whale? They said, let's blow it up. And this is what happens. So I think we've still got, it's not going to work now. So it's a bit dodgy.
No, it's still
Definitely not electronic detonation.
It had to be said, the Oregon State Highway Division not only had a whale of a problem on its hands, it had a stinky whale of a problem. What to do with one 45-foot, 8-ton whale dead on arrival on the beach near Florence? It had been so long since a whale had washed up in Lane County, nobody could remember how to get rid of one. In selecting its battle plan, the Highway Division decided the carcass couldn't be buried because it might soon be uncovered. It couldn't be cut up and then buried because nobody wanted to cut it up, and it couldn't be burned. So dynamite it was, some 20 cases, over a half-ton of it. The hope was that the long-dead Pacific gray whale would be almost disintegrated by the blast, and that any small pieces still around after the explosion would be taken care of by seagulls and other scavengers. Indeed, the seagulls had been standing nearby all day. As everything was being made ready, we asked George Thornton, the highway engineer in charge of the project, for his final observation.
Well, I'm confident that it'll work. The only thing is we're not sure just exactly how much explosives it'll take to disintegrate this thing so the scavengers, seagulls and crabs and whatnot can clean it up.
Is there any chance it might be more than a one-day job?
If there's any large chunks left, and we may have to do some other cleanup, possibly set another charge.
The dynamite was buried primarily on the leeward side of the big mammal, so that most of the remains would be blown toward the sea. About 75 bystanders, most of them residents who had first found the whale to be an object of curiosity before they tired of its smell, were moved back a quarter of a mile away. The sand dunes there were covered with spectators and land blubber newsmen, shortly to become land blubber newsmen, for the blast blasted blubber beyond all believable bounds. Our camera stopped rolling immediately after the blast. The humor of the entire situation suddenly gave way to a run for survival as huge chunks of whale blubber fell everywhere. Pieces of meat passed high over our heads while others were falling at our feet. The dunes were rapidly evacuated as spectators escaped both the falling debris and the overwhelming smell. A parked car over a quarter of a mile from the blast site was the target of one large chunk. The passenger compartment literally smashed. Fortunately, no human was hit as badly as the car. However, everyone on the scene was covered with small particles of dead whale. As for the success of the effort, well, the seagulls who were supposed to clean things up were nowhere in sight, either scared away by the explosion or kept away by the smell. That didn't really matter. The remaining chunks were of such a size that no respectable seagull would attempt to tackle anyway. As darkness began to set in, the highway crew were back on the beach burying the remains, including a large piece of the carcass which never left the blast site. It might be concluded that should a whale ever wash ashore in Lane County again, those in charge will not only remember what to do, they'll certainly remember what not to do.
Yeah, it's quite funny. So actually blowing things up like that is a serious matter, because you may have remembered heard.
That was started. So, this one's even better.
Is it doing it again?
It's not the only place to offer zoology, but it's one of the few to offer
We've got to kill it, don't we?
sciences course. It really offers.
Do we know that?
Just close the window.
Yeah. You may remember that in Canberra there was that hospital they were going to.
Oh, Canberra Hospital,
Yeah, so, well, they shouldn't have had spectators were too close, but actually they just got the calculations wrong in terms of how much they needed to drop the building. So these things do go wrong. Okay. Yeah, well, I hope you found that useful.
Very good.
Yeah.
Yeah. Very good.
Thanks, Mike.
Yeah.
Thank you.
Thank you for the help.